So I'll try a little bit of storytelling of what happened in the Monty project so far and where we're at right now and how we got there. And yeah, for brevity, I'll focus on the parts that I was involved in, which is the graph learning parts. But it obviously doesn't cover just things that I did on my own, but it was a huge team effort to get there. So yeah, let's get started.
Sounds like this is the follow-on to the Tears of Blood.
Yeah.
Oh, that's pretty cool. New Pick Island.
New Pick Island. How sick were you?
Oh,
So,
Fever induced.
so once upon a time, the Monty team washed up on the shores of New Pick Island. They figured the first thing they had to do was to get oriented and figuring out how to use their compass. This meant to draw up the building blocks of the intelligent system they were imagining.
Yeah.
So we drew up the basic principles inspired by the brain and the thousand brains theory. One of the principles is to use sensory motor learning and inference. So sensing an object and sensing the world is an active process of moving around and sensing the world. Second principle was to use reference frames and not just a bag of features. Another principle is to use a modular structure. We don't have just one input image and no sensor perceives everything at once. We have multiple sensors that each perceive small patches of the environment and they can move around and they can communicate with each other through voting, which brings me to the next principle as a communication protocol, which makes the whole modular structure possible so that every module can communicate with every other module. They all speak a common language, no matter what's going on inside of the modules. Here's another high-level overview. I won't get into too much detail of how this looks like. But
I think we just fast-forwarded about 400 years ago. we lost our ancient motifs here.
Yeah, I'm sorry. I kept the font. So the basic building blocks we envisioned were to have sensor modules and learning modules. And sensor modules can be modality specific, so that can be for touch or vision sensors, for example. But then what they output is unspecific to the sensory modality and can be the input to any of the learning modules, and it includes features and information about movement and location in space. And these learning modules can then communicate with each other through lateral voting or hierarchical connections to other learning modules. And another essence from the principles before is that these learning modules use reference frames for the models that they build. They used their compass to reach the nearest town. Then they took a break to set up an environment in which they could test their ideas.
Great.
So I won't get into too much detail here either, but Ben nicely set up this great code framework where each of these boxes here is a class that can be customized individually. So we can write custom sensor modules, custom learning modules, and so on, all building on these principles that I just named. And this code framework is basically the basis of everything ahead to come. And yeah, thanks a lot to Ben for setting up this really, really nice framework. And then Louis set up the habitat environment where we have 3D object in space, and we can have different sensors. For instance, here we have a camera, which can move in space. And since we have this principle of small sensor patches, this is in the middle, we see what the sensor patch is actually perceiving, and it can then move in the world across the object to build up a coherent picture of the image and build a 3D model of it. And what we use for most of our experiments is the YCV dataset, which contains 77 household objects that are shown here. With the framework and environment set up,
We got sound effects.
yeah, I continued onwards to work on the first prototype. They set up the first learning module, which could recognize objects independent of location and translation by using displacements stored in graphs. So the displacements that we use here to recognize objects are the gray lines in here. So basically how we move from one location to another location. And since these displacements can be represented rotation and translation invariant, we achieved this invariant object recognition, where we can move along the object with our sensor patch. And through these displacements that we're sensing, we can recognize which object we're on and where on the object we are. However, their system relied on sampling the same displacements as stored in the model. So if we sample different displacements, so movements that are not corresponding to any of the gray lines that are stored here, this approach did not work. So they continued their journey. After a long walk through the forest of smaller and larger issues, they came up with a new learning which avoided this problem. They spent some time in the next town tweaking and improving this module. So this new learning module is what we used for the past months until very recently. It relies on storing locations and then taking displacements as input and rotating these displacements to try and fit the 3D model. And with this mechanism, we can still recognize objects rotation and translation invariant, but now we can sample arbitrary displacements. So let's take a bit of a closer look at it, how this works. Basically, we learn an object in an arbitrary orientation by moving the sensor around it. Like mentioned before, each learning module receives features from a small patch of input and learns its own model of the object. And then features can be pose-specific, like point normal and curvature directions, which are shown here as the green and red and orange lines, which means pose-specific means if the object rotates, these features will also rotate. We can also have pose-unspecific features such as color or the magnitude of curvature, which do not change if the object is rotating. We use the pose features, so these three vectors I just showed, to initialize the hypothesis space of possible object locations and rotations. And basically the rotations are tied to the different locations on the object. So if I would be on the top of the can here, the rotation of the can is exactly 180 degrees rotated from if I would be on the bottom of the can, and 90 degrees rotated from if I would be on the side of the can. Then we use this hypothesis space to test them using observations that are made in like successive observations to eliminate hypotheses. So first we use the pose-independent features such as color and curvature to determine the possible locations on the object. So for instance, here we're sensing like a very curved ridge on a yellow object. So we think we could be on any of these green locations in the model. And then we use the pose-dependent features to determine the possible rotations at each of these locations. So saying if I'm sensing these light-colored displacements, pose features, and I would be at this particular location where I have stored these vectors, then I would have to rotate my sensed vectors a certain amount to align them with the ones that I've stored in the model, and that would be the rotation of the object. And we do this over successive observations until we've eliminated all hypotheses except for one, and that would be the object and pose that we detect. Okay. Now we can detect objects independent of the displacements that are stored in the model. They continue their journey and decide that it is time to add voting into their system. They add voting on object ID and pose, which helps achieve faster inference and more robustness. So if we do not vote, the model needs more steps than if we actually vote between multiple learning modules that each receive sensory information from a slightly different patch on the object. Next, they decide to tackle the sample. Oh, sorry.
Could you go back?
Yes.
Okay, 5 learning models, no vote, 5 learning modules, opposed, 90 vote, vote plus TC, 3-5, what's that?
That's about the terminal condition. So basically saying if one of the learning modules has recognized the object, then all of the other ones just.
Okay, so
take
we're still voting, the rest of that voting stuff got truncated and we're still, okay, got it.
Yeah, exactly. So next they decide to tackle the sampling problem. So far we could recognize the object independent of the displacements that are stored, but if we sample new locations on the object, it still caused some problems most of the time. So they have seen this on the horizon for a while now, but it is finally time to tackle it. They develop an evidence-based learning module. This learning module does not discard hypotheses based on inconsistent observations, but instead updates the evidence count for these hypotheses. So before we had a list of hypotheses, and whenever we get an observation that's inconsistent with one of these poses or objects, we remove it permanently from this list of hypotheses and it cannot be recovered. And now in this new learning module, we keep all of the possible hypotheses and update the evidence for each of them at every step. So for each hypothesis, we calculate the evidence based on stored points in the model in a certain radius. So for instance, like this red radius here would be what we use for most of experiments. And yeah, using the observed features to update the evidence. And for this, we use, for one, the morphology error, which is the distance weighted angle between the pose features. This can add and subtract evidence depending on how high this error is. Optionally, we can add evidence if pose independent features such as color match with what is stored in the model. This is also distance weighted. And then we have an evidence decay factor, which is applied to all of the hypotheses at every step to push the evidence towards 0 and not have it grow too large. And then additionally, we could, if we have multiple learning modules and sensors, we can also receive evidence through votes, which is also distance weighted. All of this can be done with efficient matrix multiplications, which makes this, yeah, actually faster than the previous learning module. The new model outperforms the old one in detecting the 78 YCB objects. So the old one reached, on the full data set, it reached performance of about 84%. And the other episode ended either in detecting the wrong object or having no object that matches. And now we have a performance of about 93%. And most of the other episodes end in a timeout because we have a pretty inefficient action policy, which is just a random walk. And the YCB data set actually is, yeah, includes a lot of symmetrical objects and ambiguous views of objects. So most of these timeouts, if you look at them, they are very reasonable why the module couldn't find a correct solution there. Also in this learning module, voting cuts down on the number of steps needed to recognize an object. So again, here, no vote, and here with voting. And actually it cuts down a lot faster than with the previous learning module while not affecting the performance. Okay, so they take a short trip to a small seaside village to perform an extensive robustness evaluation on the new learning module.
That's where you live, right? Aren't you on the seaside?
Yes. The new evidence learning module works surprisingly well. They tested on a range of scenarios, including new sampling. So here we have in green the new module and in blue the old one. And on the left side, we have the performance when we sample approximately the same points, which is 100% performance. And then on the right, we have two different scenarios where we sample new points, completely new points. And the old learning module degraded in performance if we sample new points, while the new one pretty much retains the performance. We also tested rotation and translation invariance again, which seems to hold up pretty well. So rotating by 1 or 10 degrees from how the object was learned still works quite well, and also moving the object in space. Change in sensory modality. So here we use the touch sensor that Philip implemented. And basically we learn a model using the camera, so the vision sensor, and then we try to recognize the object with the touch sensor. The old learning module couldn't do this at all, and the new learning module does quite well at this. And then also sensor noise, so adding some Gaussian noise to the detected features and locations. This pretty much ruined the performance of the old learning module, but the new one using evidence still reaches 100% performance, which again makes sense because if we get one inconsistent observation, we don't just discard the hypothesis, it just receives less evidence. And we can still recover it with more steps. On the way back, the test crew makes a short stop at the cave of generalization. Here they find that the amount of evidence received for each object model can tell them about object similarities. So here we look at the end of each episode, what is the evidence for each of the objects in the YCP data set, and then do a clustering of this evidence matrix. And we can see that we form some meaningful clusters. So for instance, if we zoom in on this orange one on the left, we see it clusters round objects, and then also within this smaller cluster here, we have round and yellow-orange objects. If we look at another cluster here, we have a cluster of cups, which are actually also sorted by color. So first here, the ones here on the left are yellowish orange cylindrical shaped objects, and then we go further in the cylindrical shaped objects through the red colors and then to the blue colors. And then also the other clusters seem kind of meaningful. So here we have ball shaped objects like golf ball, apple bowl, baseball, and so on, marbles. We have elongated objects like the fork, spoon, and spatula. We have airplanes, and we have boxes and bricks. Also, if we present the object with present the module with an object that it has not learned about, it retrieves the object that seems to be most similar to it in its database. So in this case, the picture on the left shows an object that the module has never seen before. So for example, a mug. And then we look at which is the object that receives the highest evidence. And in this case, it would be this cup that's also red. Here it's like two different cups that have slightly different color. If there is no object that is that similar, it still seems to be reasonably close. So here the picture base is a cylindrical blue object, and it the object that receives the highest evidence count would be the master chef can if it doesn't know about this object here.
This looks like it's being heavily biased by color in this case.
It looks like that, but I
Yeah.
don't think so, because it's color and shape, because it
Yeah,
happens.
For
It's
example,
picking up the red cup if you give it the red mug, but it's not picking up the red apple.
Yeah.
And so it's using both.
Yeah, and it's just that this is the closest. It's not saying that like other cylindrical objects don't have any evidence. It may be that all of these cylindrical objects have a higher evidence, but the blue one has the highest one because it also matches in color. But for example, here the marbles, if we don't have a small round red object, the highest one would be this golf ball, which is actually white, but it still has a similar size and curvature and shape. Okay. Back in the evidence LM town, we look back at what we have accomplished so far. We have implemented the Monty framework, set up a test environment, have achieved rotation, translation, invariant recognition, sampling arbitrary displacements, voting and speed improvements, sampling invariance, robustness, and some basic generalization. This was a short summary of the path the Monty team has taken to end up here. Of course, many details were left out. Over time, we have sent out several search parties to explore other routes. We have implemented alternative approaches such as temporal memory, ICP, and HDCD. The travelers have dealt with many struggles along the way and learned new lessons daily. Our path was windy and long, but we kept following our compass and moved one step in the direction every day until we ended up here. The evidence LM town is a beautiful place, and we may spend a while test all the new capabilities and regroup. But what's up ahead? So Niels has already started forging ahead into the fog, getting started on implementing some more intelligent action policies. Like I mentioned earlier, right now we're using a pretty random policy to move along the object, which is not very efficient. So we can really make this a sensory motor system by making the policy actively test hypotheses and seek out features that will help them recognize the object faster. We've also had several brainstorming meetings lately talking a lot about hierarchy and how this could be implemented. Another thing further in the future would be attention, especially if we have many learning modules that communicate with each other. We may not want to pay attention to everything at once and have everyone talk to everyone else. Also, so far we've dealt with one object in an empty void, but we would want to be able to tackle multiple objects in a scene and occlusions. Additionally, the objects right now are rigid objects that do not transform and do not move, but we would want to be able to cover object behaviors and transformations. Further out, we would also like to have continual self-supervised learning. So not currently we're doing some weekly supervised pre-training before we test these object recognition capabilities, but learning from scratch with very weak supervision continually would be nice. And then further out in the fog is like representing non-3D concepts or dealing with two-dimensional images or other more abstract conceptual structures. The end of chapter 1.
Oh, that's a great
Version of this.
That's
great.
Yeah, it was really
Great,
great. It was fun, nicely done, also really had a lot of great content. And surprisingly to me, I think the fun wrapper you put it in made it easier to understand.
Yeah, very nice. Thanks for you.
We need,
You created a reference frame for the Monty story.
Yeah, it's
Yeah,
interesting.
New Pig Island.
Yeah.
As opposed to like just a temporal sequence of slides, if you put them on an island at locations, it's a little easier to know.
right, yeah.
It's like the memory
That's
palace.
right, right. And of course, you need to add avatars that look like us. You start with yourself.
Army.
There you go. Just, you can start with, in our medieval costumes, right?
Yeah,
And how about-
in the
How
in the
about a
very
soundtrack
beginning,
too?
I made some pictures with the DALL-E, like this picture here,
Oh, you used about
this
dollars for
picture
that?
here.
Really?
But
Wow.
yeah, it was just a bit, it didn't really work that well, so I kind of gave up after the first.
Well, at
two.
Halloween, you left some more opportunity. That's another conversation.
That was great.
It's
And the
excellent.
work is great. And I'll say one more thing. I really appreciate you starting off with the principles in the beginning again. So we don't forget those.
Yeah, I mean, yeah, I feel like that's really been our compass.
I know, but it's
whole
so
journey.
easy, it's so easy to forget that stuff. So, I just want to say, appreciate it.
I had one question. Could you talk about your algorithm you're using for evidence decay?
Just for the decay factor or for the whole learning module?
Well, is it just, you advance it by the number of steps, or what's the axis on the decay? What's making it decay? Just the fact that haven't gotten evidence recently, or what?
Right now it's pretty simple. It just takes the current evidence factor and then it's like if the evidence is negative, it adds a little bit of evidence, and if it's positive, it subtracts some. And the further away from zero it is, the more it adds or subtracts. So it pushes it towards zero over time. But it's one of the things that still kind of need to be tweaked a little bit. So it's still, the evidence can still grow quite high. Yeah, it's not a working idea.
My thinking was that if you're exploring an object and you develop some evidence, and then you start exploring a different section of it so that that particular body of evidence doesn't get refreshed while you're kind of concentrating on some other aspect of it, does it really want to decay? Or, I mean, if you're getting negative evidence against it, that makes sense, but I was just kind of worried that you're decaying it because you haven't seen anything for a while.
Yeah, so I guess right now that doesn't really happen because we always see something. But yeah, I guess at the moment the decay factor is mostly just to keep the evidence count in a certain range because we're not normalizing it. But yeah, I'm not sure yet what the best way to do this would be.
I wonder if this addresses kind of what Kevin's saying, like, because I guess, yeah, the evidence doesn't sort of stay with that part on the object. It kind of moves with the new displacement. So
Yeah,
you're not gonna, like, as long as you're still on the object, it's not gonna decay.
Yeah.
Okay.
Maybe we can take, in a future research meeting, you can go into some of this in more detail again.
Yeah.
Great, thank you.
Thank you.
Thank you.
Thanks.
Yeah.